Unit 7 on electromagnetism for Year 13, and this lesson is on mutual inductance and transformers. Now, the term mutual inductance implies there's more than one thing happening here. So, mutual inductance involves two coils placed close to each other. When a steady current flows in one coil, a magnetic field is produced in the other coil. But since there's no change in flux, no voltage will be induced in the second coil. However, if the switch is opened or closed, there will be a change in flux, and hence a voltage will be induced in the second coil. Now, the change in current in one coil affects the current and voltage in the second coil, and this is called mutual inductance. And the size of flux is proportional to current. So, the formula for flux is M delta I, and the negative sign is for Lenz's law. So, and the voltage that's induced in the second coil is given by this formula. Now, this formula is not there in your standard. However, the concept of mutual inductance is there in your standard. Transformers. Now, transformers is an example of mutual inductance where a changing current and hence changing magnetic flux in the primary coil causes an induced voltage in the secondary coil. And what we just saw, this is the size of the induced voltage in the secondary coil. So what do transformers look like? So you've got an iron core with two sets of coils, one round the core. One of them, the primary, is what's connected to the supply, and the secondary is it's not connected to a supply, but you want an induced voltage in the secondary coil. Now, the iron core is laminated to reduce eddy currents, which would cause excess heating and energy loss. Now, providing all the flux from the primary links to the secondary, we have this formula that connects the voltage across the primary, the voltage across the secondary, the number of turns of the primary, and the number of turns of the secondary. Now, there are three types of transformers. There is a step-up transformer where the number of turns of the primary is less than the number of turns of the secondary, and hence the voltage across the primary is less than the voltage across the secondary. Now, you have a step down transformer, which is the opposite. You want a smaller output voltage, so the number of turns of the primary is bigger than the number of turns of the secondary, and the voltage of the primary is larger than the voltage of the secondary. And you have the third type called an isolating transformer, which is used in places where a gadget could get wet. So it doesn't, the number of turns are the same, and so is the voltage. What it does is that it prevents electric shocks. Now, in an ideal transformer, no energy is lost, so the power output is equal to the power input. So power is V times I, so VPIP equals VSIS, and the efficiency has to do with how much you get out compared to what you put in, times 100, because efficiency is always expressed as a percentage. Now, how can you increase efficiency? You can do that by reducing heat loss. So you can have thin laminated sheets of iron that forms the core, and you can use copper wires as well as an iron core. What does the iron core do? Iron is magnetic, so it guides the lines of flux from one to the other.